In mathematics, a local field is a special type of field that is a locally compact topological field with respect to a non-discrete topology. Given such a field, an absolute value can be defined on it. There are two basic types of local field: those in which the absolute value is Archimedean and those in which it is not. In the first case, one calls the local field an Archimedean local field. In the second case, one calls it a non-Archimedean local field. Local fields arise naturally in number theory as completions of global fields. Every local field is isomorphic to one of the following Archimedean local fields: the real numbers R, and the complex numbers C. Non-Archimedean local fields of characteristic 0, finite extensions of the p-adic numbers Qp. Non-Archimedean local fields of characteristic P, finite extensions of the field of formal Laurent series Fq over a finite field Fq. There is an equivalent definition of non-Archimedean local field. It is a field that is complete with respect to a discrete valuation and whose residue field is finite. However, some authors consider a more general notion, requiring only that the residue field be perfect, not necessarily finite. This article uses the former definition. Induced absolute value. Given a locally compact topological field K, an absolute value can be defined as follows. First, consider the additive group of the field. As a locally compact topological group, it has a unique H measure μ. The absolute value is defined so as to measure the change in size of a set after multiplying it by an element of K. Specifically, define Kr by for any measurable subset X of chi less than infinity. This absolute value does not depend on X nor on the choice of H measure. This definition is very similar to that of the modular function. Given such an absolute value on K, a new induced topology can be defined on K. This topology is the same as the original topology. Explicitly, for a positive real number M, define the subset Bm of K by then, the Bm make up a neighborhood basis of 0 in K. Non-Archimedean local field theory. For a non-Archimedean local field F, the following objects are important. Its ring of integers, which is a discrete valuation ring, is the closed unit ball of F, and is compact. The units in its ring of integers which forms a group and is the unit sphere of F. The unique, non-zero prime ideal in its ring of integers which is its open unit ball. A generator of called a uniformizer of F. Its residue field which is finite. Every non-zero element of F can be written as R equals nu with U a unit, and n a unique integer. The normalized valuation of F is the surjective function v. Fz infinity, defined by sending a non-zero to the unique integer n such that R equals nu with U a unit, and by sending 0 to infinity. If Q is the cardinality of the residue field, the absolute value on F induced by its structure as a local field is given by an equivalent definition of a non-Archimedean local field is that it is a field that is complete with respect to a discrete valuation and whose residue field is finite. Examples: the p-adic numbers. The ring of integers of Qp is the ring of p-adic integers Zp. Its prime ideal is Pzp and its residue field is Zpz. Every non-zero element of Qp can be written as Upn where U is a unit in Zp and n is an integer, then V equals n for the normalized valuation. The formal Laurent series over a finite field. The ring of integers of Fq is the ring of formal power series Fq(T). Its prime ideal is and its residue field is Fq. Its normalized valuation is related to the degree of a formal Laurent series as follows. The formal Laurent series over the complex numbers is not a local field. For example, its residue field is C(T equals C), which is not finite. Higher unit groups. The nth higher unit group of a non-Archimedean local field F is for n1. The group U is called the group of principal units, and any element of it is called a principal unit. The full unit group is denoted U. The higher unit groups provide a decreasing filtration of the unit group whose quotients are given by for n1. Structure of the unit group. The multiplicative group of non-zero elements of a non-Archimedean local field F is isomorphic to where Q is the order of the residue field, and μQ-1 is the group of saint roots of unity. Its structure as an abelian group depends on its characteristic. If F has positive characteristic P, then, where n denotes the natural numbers, if F has characteristic 0, then, where a 0 is defined so that the group of P power roots of unity in F is higher dimensional local fields. It is natural to introduce non-Archimedean local fields in a uniform geometric way as the field of fractions of the completion of the local ring of a one-dimensional arithmetic scheme of rank 1 at its non-singular point. For generalizations, a local field is sometimes called a one-dimensional local field. Depending on the definition of local field, a zero-dimensional local field is then either a finite field, or a quasi-finite field, or a perfect field. From the geometric point of view, n-dimensional local fields with last finite residue field are naturally associated to a complete flag of subschemes of an n-dimensional arithmetic scheme.